So today we're going to be looking at bonding, and the question that we want to be asking is, why do atoms form molecules with other atoms? And it's a very simple answer. Atoms are trying to fill the outermost energy level. We're going to refer to that by a word called the valence energy level. And most atoms have too many or too few electrons in their valence. You might remember from chapter 5 seeing some pictures that looked like this or like this. And we said that in the end, all atoms are trying to end up looking like this guy. And so that means that they'll share electrons, they'll swap electrons, they'll steal electrons, they'll do whatever they have to fill the valence and end up looking like, like this guy, the rock. That's why noble gases, who already look like the rock, are inert. They don't react. And so in the web quest I asked you to try yesterday, we looked at 3 types of bonding, and we're going to focus on 2 types today. In covalent bonding, this is where atoms share electrons. You might even see it in the word covalent, meaning that they are shared between multiple valences. And remember that we're going to be abbreviating electrons with this symbol, E negative. So in covalent bonding, electrons are shared. I guess it depends on how you look at it, but let's go back to one of the scenes from the web quest that we tried yesterday. And so it says, before we start explaining how covalent bonds work, let's experiment with 2 atoms that will form a covalent bond to see what happens. In the box below are 2 hydrogen atoms. Try moving them around to see how they interact. So if you did this, hopefully you saw that what's going on is, as these atoms approach each other, their electrons aren't just attracted to each exclusive atom. They're attracted to both. And that means that the electrons are pulling on the protons of both atoms, and that's what holds these together. Notice I can drag them around in whatever way I want. I can't really push them any closer together because, of course, the protons are all like charges and they repel. But I can drag these around quite a lot without them separating unless I really add a lot of force. So this is a fairly strong bond, and it is simply because these atoms are sharing electrons or fighting over them. The nuclei are trying to get access to both. And so the electrons are actually spending equal amounts of time relative to both nuclei. In contrast, ionic bonding, the electrons aren't shared at all. In fact, we might say that electrons are stolen. Or we might say that electrons are swapped. But they're not shared. One atom gets control of all the electrons. You might have seen this yesterday in one of the other web quests. So there. One of the first steps in this ionic bonding web quest was the step where we were trying to find out how ions with opposite charges behave. Remember that ions are atoms that have lost or gained electrons. And if we drag this negatively charged ion close to this positively charged one, they attract each other. So there's a fairly strong attraction just because they have opposite charges. In this situation, we have a sodium atom from group 1 with an extra valence electron that it wants to get rid of. And we have chlorine, an atom from group 17, which is 1 electron short of being a noble gas. So the sodium is trying to get rid of 1, the chlorine is trying to add 1. It's a match made in heaven. The electron gets yanked from the sodium atom, and the chlorine takes it and becomes a negatively charged ion. The sodium is now a positively charged ion, and because they are opposite charges, they attract. And this is a very strong attraction, much stronger than in covalent bonding, called an ionic bond. So the question we want to ask is, what decides or determines if a bond is ionic or covalent? And we might rephrase this question by saying, who wants the electron more? So let's go back to a table that we saw back in chapter 5 that actually tells us who wants the electron more. And here is how we determine that. A word called electronegativity. And you might remember a table from way back in chapter 5 that looks like this. This is a table of electronegativity. Let's say that an electronegativity is an atom's desire for an electron. Another word would be how hard is the pull? How badly does that atom want that electron? And so it's a numerical value going from 0 to 4. Fluorine's is the highest. Francium's is the lowest. We know that because we saw that in chapter 5. We're going to ignore the noble gases for now. So what determines whether a bond is covalent, where the electrons are shared, or if the bond is ionic and the electrons are stolen, is determined by the difference in electronegativity. We're going to call that by a slightly different name. So bond character is determined by the difference in electronegativity. Which atom has the greater pull? We're going to abbreviate this with a Greek letter delta, En. This Greek letter delta right here, this guy, it means change. So the difference in electronegativity is what is going to determine whether or not our bond is covalent or ionic. I'll show you how it works. It's really simple. So all we're going to do to determine whether a bond is ionic or covalent is look at the difference in electronegativity. And this chart is how we do it. If we find the difference in electronegativity and it's between 1.7 and 4.0, that is going to be an ionic bond. And in a bond like that, the electrons are stolen. Anything that's less than 1.7 and the bond will be covalent. And there can be some differences in the types of covalent bonds, but we'll get to that in a little bit. So let's try a couple of examples and I'll show you how we do this. So let's go back to this bond between sodium and chlorine that we saw back in this web quest that we did. And from our table of electronegativities, we have sodium with an electronegativity of 0.9, and we have chlorine with an electronegativity of 3. Let's calculate the delta En. All we're going to do is find the difference. That means 3 minus 0.9, and this is a difference in electronegativity of 2.1. That puts it right in ionic bond territory. It means that the bonding is ionic, and the electrons are not shared. That means that the one with the higher electronegativity, which of course would be chlorine, gets them all the time. We saw that exactly in that web quest that we did. And in practice, that's exactly what's going on. Here is our sodium atom. If you remember, it's got an electron configuration of 3s1, meaning it has 1 electron in the valence. And of course, chlorine is an electron configuration of 3s2, 3p5, meaning it has 7, 2 in the 3s and 5 in the 3p's. And to fill the valence of chlorine, it is just taking the electron from sodium, and we get this ionic bond. What about this situation where we have these two hydrogen atoms And it's clear that those atoms are sharing those electrons equally. The definition of covalent, how does that work? Well, let's take a look. We said that in covalent bonding, the electrons are shared. Well, we were looking at our two hydrogen atoms, and they each have an electronegativity of 2.1. So if we were going to calculate the electronegativity difference and compare it to this chart, what do we get? So, plugging them into our equation, delta En is equal to 2.1 minus 2.1, and of course that's a delta En of 0, and that puts it down here. A difference of electronegativity of anywhere from 0 to 0.3 is something called a nonpolar covalent bond. In a nonpolar covalent bond, the electrons are shared totally equally. It means that both atoms get equal access to electrons, and it means that neither one of them gets the electrons more often than the other. So what happens if the difference in electronegativity is somewhere between nonpolar and ionic? Let's take a look. Here's a molecule that should be familiar to all of you. This is our old friend water. And a water molecule consists of 2 hydrogen atoms and 1 oxygen atom. And if we are looking at our periodic table, we know that hydrogens have an electron configuration of 1s1, meaning they've got that 1 extra electron that they're trying to get rid of. And oxygens have an electron configuration that ends 2s2, 2p4, a total of 6 electrons, meaning that to get that outermost energy level, they need 2. So how does this work? If we look at our electronegativities of hydrogen and oxygen, we see that hydrogen has an electronegativity of 2.1 and oxygen's is 3.5. That means oxygen's got quite a bit stronger pull on our electrons than our hydrogen. And according to our chart, if our difference in electronegativity lands between 0.3 and 1.7, that's a covalent bond that doesn't share the electrons equally. I'll show you what that looks like, but first let's calculate our delta En. So for the bond between hydrogen and oxygen, if oxygen has an electronegativity of 3.5 and hydrogen is 2.1, this is an electronegativity difference of 1.4. That makes this a polar covalent bond. What does this mean? When it's a covalent bond that is polar, it means that the electrons are shared. But not equally. It means that the atom that has the higher electronegativity is going to hog them. And that means that they end up spending more of their time around the oxygen atom than the hydrogen atom. This is going to lend what we call a polarity to this bond, because we'll end up with the oxygen having the electrons more often. That makes this a more negative atom than the hydrogens, which don't that get them as often. And that's where our polarity comes from. And we see that here in this little shape from our chart, that in a polar covalent bond, one side of the molecule gets the electrons more often than the other. Okay, take it for a spin.